Okay. So if we parallelize these instruction, you can see that we can complete the entire instruction in 14 nanoseconds, right? Assuming that each of these cycles take 2 nanoseconds. So 2 nanosecond here, 2 nanosecond here. We have 1, 2, 3, 4, 5, 6, 7. So within 7 clock cycles, we have finished 3 instructions here, right? Whereas if we did it this way, if we have done it this way, then this would take 2 plus 2 plus, okay, maybe it has different numbers, right? So we have a load, we have a store, and we have a R-type instruction. So 8 plus 7 plus 6, 3 instructions, then 8 plus 7, 15, plus 6 is 21, around 21. So you immediately see that we are saving time. 21 nanoseconds if we run them individually, but if we parallelize them, then it comes down to 14 nanoseconds. That's why we parallelize and use multi-cycle instead of a single cycle. Any questions on this? Okay, but there are some challenges when we do pipelining. So we will look at the challenges. So the challenge seen here is like, I will describe the challenges. There are basically 3 challenges, but what you have to know is in order for the pipelining to work, you need these latches. So sometimes what these do is they store values. So store values, and when you need them, you can pass them over. So when you have these latches, for each stage, you have saved values. And if we play it in, if we play the presentation. So duplicate. So you can see that we are going through different stages, and in each stage, we are using this this one-dimensional strip to save values, and that will come in handy to remove some challenges that we are going to see now. So one thing is, when we have these saved values, this is wrong because we have to make decisions whether we are going to use these saved values or not, right? So we have to use these saved values in some cases. So that's why this is wrong, and the correct solution is you sometimes need to make a decision whether you are using this value from this mux over here, or whether you are going to use the saved values. Is it being, so now it's being recorded? Yes. So there are some animations here. I looked at them. They're not bad, but very complicated animations. But if you are interested, you can look at these animations. But what I have found is these nice tutorials by a professor from University of Utah. So I was looking at these tutorials, and I was wondering, why is this guy so good? And then I went to check that his research is basically on computer architecture, and he's a professor. So yeah, so these videos explain it really nicely, but I'm going to go over these topics now. So you have these nice tutorials here. And also another thing I'm just going to show you is this professor, he has taught computer architecture for both an undergrad course and a graduate level course. So that means master's and PhD. So if we just go to one of the links. So if you go to this person and go to playlist, he has these 2 lectures on computer architecture. This is for the undergrad computer architecture course, and this is for the master's and PhD computer architecture course. So like in your undergrad, you are taught the basics, right? But if you want to learn more, the world is the limit, the sky is the limit. So if you find some interesting things you want to learn about, this guy goes into a lot of different topics that haven't been covered in this course. So I believe this is a good resource, and you have it in the slides. Okay, so going back to what we are going to cover in today's lecture, it is pipelining hazards. So in total, we basically have 3 pipelining hazards that we need to be aware of. And if I give you a summary, structural hazard is if you're using the same hardware. So like if you are using this IF, right? You are using the decode, and at one point you will be using this. So decode, execute, memory, and then write back. So you run this. There's one here. Here you have to use the memory, because memory uses the memory, and fetch also fetches an instruction from the memory. So that's a structural hazard. Structural hazards are if you have problem using the same hardware. What data hazard is let's say you do an add operation, right? Add T1 and something, and then you use a sub operation, but here you're using this same register, right? So you have to make sure that T1 is correct, or else you can have a data hazard where you will use the wrong value of a T1 because it has been updated in the last instruction. Control hazard is if you're jumping or branching. So if you're using BNE or jump, right? If you have already started the next instruction, you don't know whether you have to jump somewhere else, right? So that's a control hazard where you can execute instructions after jump, but you don't know if the program is going to jump or not, right? So that becomes a hazard. And one solution to solving these hazards are introducing stalling. So what stalling is, let's say you are having an instruction, right? So five of them represent one instruction, right? And then this instruction changes the value of T1, right? And the next instruction uses T1. Let's say we use T1 in the next instruction. This is instruction 2. So I2 referring to the second instruction. So one way we resolve it is using stalling. So what stalling is, these clouds that say, so one way of stopping these is if you introduce stalling. So if you have these boxes, that means you're running an instruction, right? But if you have these clouds, which means you are just waiting for something to be processed. So using stalling, you can reduce these hazards. So that's one way of doing it. It's not optimal. Basically, you're telling your hardware, stop, I need to finish something, then you can start working. So that's basically stalling, and it can be referred as these clouds. Okay. Now, when should we stall? First, let us look at the structural hazards. So here we see the example of a structural hazard where we have to fetch is from the memory, right? And use of memory also uses the memory. So if two hardwares are contending for the same action, right, then that's a hazard. How do we solve it? So the solution is we need to have hardware that can have multiple access, right? So if you can ensure that there are two access points, one access point is for memory operation and one access point for fetching the next instruction, then we won't have structural hazard. So we have solved structural hazard. Just put in more hardware, it's done. Okay. We can have another structural hazard. So there are two structural hazards. One, what you saw, is use of memory, and another one is, so write back uses the register file, right? And decode also uses the register file. So how do we solve this? Well, we need two access points. That's one solution. But another solution is we always write back at the half a cycle we use for write back. So 1 nanosecond for write back and 1 nanosecond for decoding. And how we do it is the first half is used for write back out of the 2 nanosecond, and the second half is used for the decoding. Because if we go back to this, here we see that decoding and write back takes 1 nanosecond, right? That's why we could divide 2 nanoseconds and avoid that hazard. So if in this case, the write back was, let me just clear it out for you to show. If in this case, the write back was in this portion and this portion was empty, right? Then it doesn't collide with the decoding, right? Because decoding is using the second nanosecond and write back is using the first nanosecond. That's how this structural hazard can be avoided. Any question on structural hazards? In the exam, I can ask you like, we know write back and ID use the same register file, right? How can we avoid that structural hazard? Then you have to draw this image and say, like, we are using first half for write back and second half for decoding. Another nice thing of using the first half for write back is if you have written something which changes a register, then the ID uses the updated values. So that's a nice thing as well. The decoding uses the updated values because you wrote back just one second before, 1 nanosecond before, you have the latest values, and you're for the instruction decode, you are now using the latest values. No, so now let us look at data hazards. So let's go back to what we know. We have fetch, right? We have instruction decode. We have the execution in the ALU. So this is execution. We have a memory operation. And finally, we have the write back. This is for the add operation. Now, you can see we are changing the value of S1 here, right? But immediately after, we are using S1. So this will create a problem, because if we write out how it works, mem, and then write back. We have the write back here. So when do we have the answer for add? When do we have the answer for add in the register? Can anyone say? This operation, right? When do we have S1 value updated? After which, in which step 1, step 2, step 3, step 4, or step 5? Can anyone say which stage? Yes. Step 5, yes. Because we are writing back to the register on this step, right? So if the second instruction is trying to use it, we cannot accommodate that. So one easy solution would be no, 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 no. And then again, we have to stop because drawing clouds is too hard. So I'm drawing X's. And now if we draw a fetch, decode, ALU, a memory operation, and write back. So at this point, in the first half of this, it has been written. Although in the slides, you see you have to wait 3 instructions. We know we can wait 2 instructions because you'll also see in the reference video that I gave, it's 2 instructions. You have to wait. So that's not the optimal solution. So what's the optimal solution? How do we avoid this data hazard? So the naive, like the bad solution is we wait for 2 clock cycles. We don't do anything. Say, stop, I need to do something. Then you can run the second instruction. Or the efficient solution would be, you know, that you get the result of S1 here, right? you can just pass it over. Pass it over here, then you don't have to wait. So you have to do a hardware implementation to have that, but you can actually not wait and avoid this data hazard by having the option to pass this value over. Okay. And we'll do some examples which will make it more clear. So basically, you don't have to wait if you do forwarding. If you don't have forwarding implemented, then you have to wait 2 clock cycles. Like, don't do anything, just wait for it to finish, and then you can start here. Any question on this? It will be more clear once we look at more examples. So basically, two instructions you have to wait if you don't have the forwarding implementation done. But if you have the forwarding implemented, which is also known as bypassing, you know that for the S1, you get the, so S1, what was S2 equal S2 plus S3. So S1 equal S2 plus S3, right? That happens and you get the result here. So if you just pass in the updated result using forwarding, then you don't have to wait. Okay. So here there's no wait or no stall. We learned the keyword stall, no stalling if we use forwarding. But we still have to stall even if we use forwarding if there's a load command. Because when do we have the load? When do we have the S1 ready for the load? Can anyone say? Anyone raise your hand and say when we have? It's in the image, I know, but still, it's nice if you can say it. Yes, the fourth stage, because for the load command, you have to access the memory, right? You have to access the memory. So for this, we have 1, 2, 3, 4, 5, right? And here in memory, we get the result. So if we try to run this, we need at least in the execution stage, right? There's no way, but there's no, if it was here, then we can pass it over. But no, we can't pass this. We can't go back in time. We can't go back in time. That's why for load, even using forwarding, we cannot, we have to have one stall at the minimum. So if we do one stall, then we have this. And then in the execution stage, we can get the value from here. So see, the bubbles are harder to draw. That's why you can just use X's. Okay. We need one stall. If there's a, if we have a memory operation and the next instruction is dependent on the memory operation. Basically, this is called the producer and this is called the consumer. And in operating system courses, you have producer consumer algorithms like the Peterson. You will learn more on that in a different course, operating systems, where you have the producer consumer algorithms. Okay. But the consumer has to wait for the producer with one stall here. Okay. So how do we do a stall? The decoder figures out that I cannot run this instruction now and sends a no op signal. And then everything turns into bubbles. That's how we implement it in the hardware. So the decoder finds out that I can't do this because I'm waiting on something, and then just stalls the operation. That's how we stall. So stalls are not good. We don't want stalls. They reduce performance, but sometimes stalls are required. In this case, after a load, if you're using that register, you have to stall. So in order to get correct results, you have to stall, but we will try to minimize stalls. Same in the case of jump, right? So jumps, you can know whether you are jumping or not in this stage, right? So you can have one stall and then tell the next what the next instruction will be here. Because you don't know which instruction to fetch, right? You can be jumping into a different region of the code. So for jump, you know after the decoding whether it's where you're jumping, right? Then you can get the next instruction, and you just need one mandatory stall here. So for this example, can anyone tell me how many stalls do we need, or do we actually need any stalls? These can be good exam questions, right? Like a picture and then two instructions, and I can ask how many stalls, and a multiple choice: 0 stall, 1 stall, 2 stall. So we are now seeing that this is the producer, right? This is the producer, this is the consumer. So the producer is changing R1, and we need the value of R1, right? So we can forward it here, okay? So we don't need any stalls. So for this scenario, we need 0 stalls because we are using forwarding. And in the questions, I will ask, we are using forwarding, okay? So in every scenario, I will say, assume we are using forwarding. So we don't need any stalls here because we can just pass the result efficiently here, okay? This is the point of production, and this is the point of consumption. So we don't have to go back in time, so we don't have to stall. Any question on this? Let's look at the next example. So in this case, the point of production is after the memory operation, right? It's here in the 4th stage, the mem stage. But we have to do this calculation, which is R1 plus the offset, right? We do calculations in ALU. We have to do it in here. So this is the point of consumption, but the point of consumption is before the point of production. So we can't go back. We can't go back in time. So we need 1 stall, so that we can push this result here, okay? So now if we have 1 stall, the point of consumption becomes we delay the point of consumption, and then there is no data hazard. This example, we are loading the value R1, right? But we are not using it in the ALU calculation. So if this was R3, then we needed one stall. But this is not R3. So we don't need the stall, because we only need to know where to store it in this stage. Wait, point of consumption is here. After we do this calculation, right, we need to know where to put it inside the memory. We need it here. Okay, so that is after the point of production, which is here. So we can directly pass it, and we don't need any stalls here. But if this was R3, okay, if this was R3, then we needed a stall. But because we do the R3 calculation in the ALU, which is here. So, but for this example, because this is R1 and R1 is changing, we don't need to stall. Any question on this? If yes. Yes, I can repeat. So R1, right? Load gets a value from memory and puts it in R1. But when do we know what's the value? We know the value when we access the value from memory here, right? So this is our point of production. We know what is the value of R1 here. We haven't put it into R1, but we, in order to be the most efficient we can be, we know what the future value of R1 is, right here. Now, where is the point of consumption for R1? It's here, because here we 8 plus R3 to find what memory location we want to, what is the memory location we want to replace in the memory, okay? So this happens in the ALU, but R1, we need it at this stage, where what is the value that we replace this memory location with. So only at this point, we need the value of R1. Okay. So that's why we can just forward the value here. But what if it was R3 here? Like, what if this was R1? What if this was R1? Do we need a stall? Yes. If this was R1, then I would need it in the ALU, R1 plus 8. I would need to do this in the ALU, right here. I would need it here. And then I cannot go back in time. So if this was R1, I would need one stall. And also you can recap this video and the video I provided. They go over this example too. So yeah. So summary. So I will provide this in the cheat sheet. So it will be nice. So if you have an add instruction or a sub instruction, you get the result in the third stage, right? So if this is the first instruction and this is the second instruction, right? Then you don't need any stalls. So in the summary, it just, if you have a R type instruction for the first instruction and second type instruction can be add, sub, load, store, you don't need stalls because the point of production is the third stage for the R type instructions. Okay. For load and store, the point of production for R1 is here, like R1 and R1, right? For storing, you need it in the fourth stage. So 0 stalls here, but if you needed R1 here, then you needed 1 stall, okay? But for R1 being used here, you need 0 stalls because you need R1 at the fourth stage to specify what location, like what value is being replaced in the memory location. So R1 is the value. You need it at the fourth stage for the store operation. But if this was R1, then you would need 1 stall. Okay. If this was R1, if that was the case, then 1 stall. But for this particular case, you don't need any stalls. For load followed by a add, sub, or a load, you are changing R1, right? Then you need 1 stall. And for practice, you can look at these instructions, follow the summary, and then you will know how many stalls do you need in between. So you can practice this. I'll provide the solution for this later. So that's for today's. Oh no, one more thing is for control hazards, right? You don't know whether you are going to jump or not, right? So what are you going to do? You can't do anything. So what you can do is like always 1 stall, right? You can do that by having a special hardware so that in the PC stage, you know whether you're going to jump or not. So if you need special hardware here, and then you can eliminate instead of 3 stalls, you can eliminate it to 1 stall. So this solution is special hardware. But you can also do a prediction. So in most cases, it has been found in 80% of the cases that if there's a for loop, is going to run. Okay, the for loop is going to run. They have some probability calculation of whether this program is going to take the branch, and in that case, you start calculating the next instructions. If your prediction is wrong, you just say, okay, my bad, I'll just jump. Okay, so that's just predicting. And then if you're wrong, you just branch. You waste some time, but it's okay. So nothing very mathematical here. Just you make predictions, you're wrong, then okay, no worries. And if you have 80% of the time running the for loop, then you assume that the for loop is going to run and start doing the things. But if you see the for loop doesn't run, then you just say, okay, forget about that, we're going to jump. So that's for this lecture. And what I'm going to do immediately after I get to the office is post the solutions for quiz 2 and post the names of the TAs. If you want to reach out regarding a specific question, then you can reach out to the TA.